everybody. Welcome back to the second part of Chapter 1 about science from Conceptual Physics, 3rd edition. I'm Mrs. Pound, and today's lecture is going to cover sections 1.3 to 1.5. Let's begin by talking about the scientific method. The scientific method is extremely effective in gaining, organizing, and applying new knowledge. So the steps of the scientific method, which I'm sure you've covered plenty of times in other classes, but let's review it again, are to first recognize a problem. I have a problem right here. My flashlight will not work. So I'm going to make a hypothesis about why my flashlight will not work. From the past, I think my flashlight will not work because it needs new batteries. So I have formed a hypothesis that is an educated guess about the answer to a scientific problem based on previous knowledge about flashlights and experiences with flashlights. So number 3 is to predict the consequences of the hypothesis. So my prediction about the consequences is that if I change the batteries, my flashlight will work. So number 4 is to perform an experiment to test the prediction. So I'm going to remove the batteries and replace them with new ones. So here go the old batteries. Here come the new batteries. And I am going to put them in my flashlight. And see if it works. Oh, it still doesn't work. Well, what's the next step? The next step, number 5, is to formulate the simplest general rule that organizes the hypothesis, prediction, and experimental outcome. So I would say that my formulation, my conclusion, a lot of times this is called a conclusion, is that it wasn't the light bulb, or it was not the batteries that don't work. So this is actually a really good example of the batteries not working. Our hypotheses are not always correct. Sometimes we have to go back to the beginning of the scientific method and start over again because our prediction was not correct. So the next thing I would probably look at is, actually with the way this is, I would probably flip those batteries around and see if it works the other way. So I'm performing another experiment. It still doesn't work. So my next hypothesis would maybe be, well, I have kids. Maybe they put used batteries back. So maybe I'll test some other batteries. Maybe I'll take a look at the bulbs. Okay, so this is an ongoing process. It's not just something that we make a hypothesis, boom, we come to a conclusion right away, problem solved. Sometimes we have to go back. And in fact, most discoveries are trial and error. This is a good example with my flashlight. I'm just trying lots of different things. It's kind of trial and error at this point to see what works. And I'm sure you've heard of the stories of Thomas Edison with his light bulb, the incandescent light bulb, and the fact that he went through about 1,000 trials before he figured out a good, economically viable, commercially viable light bulb that could be sold. The light bulb had already been invented, but he was trying to make it practical. So trial and error. Also, number 2, sometimes there's experimentation without guessing. Sometimes an experiment is performed and we just don't know what's going to happen. We have no idea. And so sometimes we don't have a hypothesis. And then there are accidents. In fact, you probably have heard of the story of how penicillin was discovered. It was an accident. There was some mold growing on cheese. That mold is called penicillium. And what was observed was that it killed bacteria with just totally by accident because there was cheese in the laboratory. And that's how penicillin was discovered. Now, we're going to talk about the scientific attitude. There are actually a number of terms that we have to make sure we understand and can keep straight. The first one is a fact. A fact is close agreement by competent observers who make a series of observations of the same phenomenon. And one thing we have to realize about facts is these are based upon observations. However, observations are fallible depending on your point of view. Maybe you don't completely understand what you're observing. So when we make observations, we have to be very careful that we are in fact writing down observations, okay, and not what we think is going on. That it actually is a true observation. And if enough people make that same observation, it can become a fact. And one thing we have to remember, though, is that they are not absolute and unchanging. As we discover more, we know better, and a fact may change. Also, we will be taking a look at a lot of laws or principles. This is a general hypothesis or statement about the relationship of natural quantities that has been tested over and over again and has not been contradicted. So this is the relationship of natural quantities. A law is something that happens over and over and over again, as something like the law of gravity. We always observe with the law of gravity that if we drop an object, it always falls. That is just a fact. Okay? So that is what a law is, something like the law of gravity. It's always going to happen. A theory is a synthesis of a large body of information that encompasses well-tested and verified hypotheses about certain aspects of the natural world. Theories attempt to explain what is going on, and they are well-tested and verified. Now, this is different from the way the term theory is used popularly today, because a lot of people have theories, which is their explanation for why something is going on. But the difference between an individual's theory about something and a scientific theory is that a scientific theory is well tested and verified. And it comes from a large body of information. A lot of data has been collected, a lot of experiments have been performed. It's not just one experiment, it's a lot of experiments in order to develop a theory, which is not true of most people's explanations of why they think things are going on. One thing we also have to understand are concepts, because we're studying conceptual physics. This is the intellectual framework that is part of a theory. So we are taking a look at the concepts behind the theories, the framework that builds up that theory when we're studying physics. Another thing we have to understand is that a scientist predicts what can or cannot happen, not what will or will not happen. That is just not possible that we know that this will happen. We can say it can or cannot happen. It is important that a scientist be both open-minded and skeptical. Windows need screens. A scientist should look at the results of their experiment, and if it contradicts what they think, they should definitely question their preconceptions. But they also have to be skeptical about it. This is where the windows need screens. Windows are open. They let everything in. But we put filters on the windows, and we need filters up. For example, I teach at a Christian school. So when we do experiments, we have to be open minded about the results. But we also have to be skeptical in that our filter at our school is, in fact, the Bible. And so if something goes against the Bible, we have to take a look at it and say, am I looking at this correctly? Okay, and use that as a filter. Now, going back to hypotheses, scientific hypotheses must be testable. So, even though they are educated guesses, they must be tested by experiment. It is not scientific unless there is a way to prove it. Let's take a look at these two statements, and I want you to determine which is the best example of a scientific hypothesis. Intelligent life exists on other planets somewhere in the universe, which is statement number 1, or statement number 2, no material object can travel faster than light. Go ahead and pause the video and take a minute to think about these before I show you the answer. If you chose number 2, you are correct. No material object can travel faster than light is the best example of a scientific hypothesis. The reason for this is we could actually test this. There's no way to test number 1, that intelligent life exists on other planets somewhere in the universe, because there are way too many planets in the universe, and we have really just barely made it out of our own solar system, let alone into our galaxy or the rest of the universe. So that just simply is not possible to test. However, we can accelerate objects, we can make them go really fast and see if they can go faster than light. So today we've taken a look at the 5 steps of the scientific method. We have talked about the difference between an observation and a fact. We have also distinguished between a hypothesis, a theory, and a law. And you should also be able to distinguish between everyday meaning and the scientific meaning of a theory. If you're one of my students, you should have your notes completed. If they're not, go back in the video and finish those up. And you should write 5 questions in your left-hand margin that you think I will ask on the test.